get into it. So calculate the observed cell potential based on the following conditions at 298K. So it says 298K, so that means, I'll remind you, we can use this version of the equation. E cell equals E standard cell minus 0.0592 volts divided by the number of moles of electrons times the log log base 10 of the reaction quotient. Okay, and so here we've got two half cells written. Oh, and I just noticed my standard cell potential did not get copied over compared to my cheater notes here. So that's supposed to be negative 0.76 volts. And of course, we could have looked it up, right? And we've used this one lots of times. I think 0.762 volts, but we'll just keep it under this number of sig figs. Okay. So now we have to decide which one of these is going to be the anode and which is going to be the cathode. And if I flip this top one, that's negative 1 volts. So when I add those together, it'll be negative. So I want to flip this reaction. Okay. So that means this is the anode. And besides, we should recognize by now the more negative value of cell potential will always be the anode. And so now I can calculate my standard cell potential by saying cathode minus anode, both written as reduction potentials. And we can see that they both are written as reduction potentials. So that's going to be, let's see here. Where did that go? Yes, 1.00 minus 0.76 volts to give me positive 1.76 volts. So I've already got that constant right there. But now what I need to do is get the number, oh, bless me, get the number of moles of electrons transferred. But I also need to be able to calculate the reaction quotient based on all of these concentrations right here, which means I need to get an equilibrium expression for this reaction, which means I need to be able to recombine these two halves into a total balanced reaction. Okay, so let's do that. So I'm going to write this one, and we can see right away that I'm going to need to multiply this by 2 because I had 2 electrons being transferred in the zinc reaction and only 1 in this vanadium oxide half reaction. So I'm automatically going to multiply that by 2. So that becomes 2 VO2 plus 4H plus 2 electrons. And that makes 2 vanadium oxides plus 2 H2O. And I'll just drop the phases for now. Okay. And then now we recognize that because we made this one the anode, right, the negative, that means we need to flip the zinc reaction. So that's going to go zinc solid makes zinc 2 plus 2 electrons. And now when I recombine these, the electrons and the electrons cancel. And now I'm going to go ahead and write the phases so I can get the equilibrium expression written correctly. Okay. And maybe I even need more room to do this problem. But let's see how it goes. So I have 2 VO2 plus aqueous plus 4 H plus aqueous plus zinc solid. And we should recognize now that this is an equilibrium reaction because I can drive these cells in the forward direction or the reverse direction. So I'm going to write that as an equilibrium reaction. And now that's zinc 2 plus aqueous plus 2 VO2 plus aqueous plus 2 H2O liquid. And now we have to remember how to get an equilibrium expression out of this. Okay, so I'm going to write that as Q because we're doing this for initial conditions or non-equilibrium conditions. Important to recognize our batteries, when they hit equilibrium, they stop working. So most of the time our batteries are not in equilibrium. So now this is going to be products over reactants, but remember I don't include pure solids or pure liquids. So now this is going to go as VO 2 plus, and of course squared, because of that stoichiometric coefficient, times my zinc 2 plus aqueous, don't include water because it's a pure liquid, and now that's all divided by VO2 plus all squared times H plus to the fourth power. And I don't include the solid zinc, once again, because it's a pure phase. Okay? And so now you can see I have all these concentrations listed here, so I can plug these in to get my Q value. And so that's going to go as the following. Don't mix up the two vanadium oxides. So we've got this one, VO2 plus. So that would be vanadium 4 oxide. And this one would be vanadium 3 oxide. Vanadium 5 oxide, excuse me. So now this one, VO2 plus, is the 0.01 molar. Let's see, I'm looking at my notes, and it looks like I didn't calculate it right in my notes. No, I did. Never mind. Okay, here we go. So the 0.010 times, and that's all squared, okay, times the zinc, which is the 0.10. And then now that's all divided by VO2 plus, so that's vanadium 5 oxide. So that's 2.0 all squared. And then now that's divided by H plus 0.5 molar to the fourth power. So I already calculated that in my notes. And so make sure that you get the same value as me, 4.0 times 10 to the negative 5 for the reaction quotient. And so now I have everything I need to finish off this calculation, which I'm going to do up here. Okay, so that's going to go as my E cell is going to equal 1.76 volts minus 0.0592 volts divided by 2. Remember, I got that 2 from the number of moles of electrons transferred. And then now that's times the log of the Q, which is 4.0 times 10 to the negative 5. So now I can say, I'll calculate it in the following way. 4 times 10 to the negative 5. And I'm going to say log log, boom. And then now I'm going to say times 0.0592 equals divided by 2 equals. And then now notice that that's a negative number, but I have a negative sign in the equation. So that's going to be a negative negative, which is going to turn that positive. So I'm just going to say times 1 negative to make my life a little bit easier. And now we'll say plus the 1.76 volts. And I get 1.89 volts. So as we can see here, if I had used standard conditions, so if I had used 1 molar of everything, I would have got 1.76 volts out of this. But by adjusting those concentrations, I actually got a little bit more juice out of this battery. Okay, and so that's why we want to be able to calculate our equilibrium, we want to be able to calculate our cell potentials based on non-standard conditions. So there's a lot of stuff going on here. So make sure you're okay with this, and we'll do some more examples of this in the live meeting.